Okay, ladies and gentlemen, let's get started. As I was mentioning at the last week, we have a total of 8 visitors over the next 4 weeks. These are candidates for 2 open faculty positions in the computer science department, one in cybersecurity and the other one in data science and machine learning. So we have our 3rd visitor, Hosna Jabari. She is the 2nd candidate for the data science position. She is going to be speaking tomorrow in John Dewey Lounge at noon. Coffee and snacks, please come and join us. Dr. Jabari is going to be talking about gene therapy. So this amazing new idea where instead of ingesting or being injected with drugs, you are injected with genes. An interesting and very controversial idea, but definitely could lead to a revolution in medicine, and Dr. Jabari is at the forefront of that area. Really interesting work, so she's going to talk about her work, which lies in the intersection between computer science, biology, and medicine. So should make for a very interesting talk. If you can make it tomorrow at noon, we'd love to see you there. Okay. Just a reminder about PyroSim. Some of you are using USB drives. Some of you have switched over to Linux and virtual machines. Some of you are on Macs. Whatever platform you are on, back up your work. I put a note on Blackboard. This is an upper level CS class. So if you come to us and say I couldn't finish an assignment or I wasn't able to do the final project because I almost finished and I lost all my code, that's not going to be a good reason for an exception. So just as a reminder, if you're using USB drives in the simulation project, down at step 16, this describes the first time that you're uploading a screenshot from your work. And right there is a note about how to save your work to the USB drive and then transfer it to your actual machine. That goes for screenshots, but also for your code itself, right? So however you do it, make sure you're backing up your code as we go. Okay. Any questions about, for the undergraduates, assignment 3, which you're working on at the moment, sensors, or grad students, assignments 5 and 6? So far, so good? Okay, so back to the lecture material then. We're working our way, we're going to finish the second of our 6 themes. This one is the tools of the trade. We've looked at artificial neural networks. We looked last time at evolutionary algorithms, and I marched you through a series of these evolutionary algorithms, beginning with simple ones, working up to more complex ones. In the later assignments, you're going to have some experience actually implementing these evolutionary algorithms, but they all sort of share one property in common, which is that they're population-based. We're taking a bunch of random solutions, which you can think of as points that are sprinkled on a fitness landscape, right? And we are then using those points to try and estimate the shape or the surface of that fitness landscape, which might be very high dimensional, might be smooth, it might be rugged, it might be smooth in parts of the landscape, but rugged in other places. And based on the heights of those points, their relative fitnesses, we're going to start to spend more time exploring spaces near higher points and delete points that are in the lower valleys, right? And we're hoping that with enough computational effort, we can get close to or find the global optimum, the best possible solution to whatever our given problem is. Okay, today we're going to switch gears and we're going to talk about physics engines. So in this class, as you've already figured out with PyroSim, you're working in Python and we're kind of hiding all the details of the virtual world and the virtual robot from you. So we're going to go inside PyroSim today and go down into the engine room of these physics engines and just get a feel for sort of how they work. So because of that, the reading for today comes from the ODE user guide. This is the Open Dynamics engine. ODE is the actual physics engine that you're using. And PyroSim is kind of like this Python robot wrapper that's sitting on top of the ODE physics engine. I picked out some parts of the user guide just to read. Some of these sections are a little bit more technical than others, but each one of these sections is going to touch on the components of physical simulation that we're going to talk about today. We will probably finish lecture 6 today, and we might move on to lecture 7, the first few years of evolutionary robotics. Any questions? Okay. Okay, so off we go. Let's start not with physical simulation first, but computer graphics. So if you wanted to create, in the old days, if you wanted to create a 2D or a 3D virtual world, you would do it in the following manner. For every object in your world, you would define its position, where is it in space, its orientation in three-dimensional space, how is it rotated in 3 space, and the shape of that object. The system would then render the scene, given all of those objects. You would then redefine the new position and orientation. And if it's a soft object that deforms, you'd also define the new shape of the object. It would render and rinse and repeat. As you can imagine, this was a very time-consuming process. And throughout the 80s and 90s, there were improvements that automated these procedures to the point where around the year 2000, the first physics engine was released, which had a very different model. Similar but different. So again, you need to obviously define the initial conditions of your scene. So for our purposes, that's again the position, orientation, and shape, so the geometric properties of the objects. But you now also need to define some physical properties of those objects, like, for example, the mass and friction properties of your objects. For now, in the assignments, we're hiding the mass and friction properties from you. Whenever you create an object, it's always 1 kilogram. Doesn't matter how big or small it is. So obviously, if you make a very large object, it's rather porous or it's rather light, or it's not very dense. If you make a very small object, it's still 1 kilogram. It's very dense and heavy for its size. And friction is relatively high. So you can think of all the objects and the ground in your pyro simulation as covered in carpet. Maybe that's the closest thing. Everything has high friction because you're going to be trying to make robots that move, so better to have high friction robots moving over a high friction surface so they can get some traction and move relatively easily. Okay, so once we've defined the geometric and physical properties of all the objects, yes?
Is it possible to play with those? Like if you wanted to try to make a skating robot or something like that?
Absolutely you can, and we'll get to that in the later assignments. You can actually start to play around with the friction parameters. We'll get to that. Okay, we define all of the objects, and then obviously we have joints as well, so we're adding in constraints, which means we're going to constrain how the objects move. If we have 2 objects that have no joints connecting them, they can change their position and orientation relative to one another arbitrarily. Doesn't matter. The minute we weld 2 objects together with a joint, happily, my lower arm cannot move away from my upper arm. It can only rotate relative to it. So every time you add a joint to your simulation, you're constraining relative motion and relative orientation of objects. Okay, so once you put all the objects in there and you've constrained the way they can move with joints, the physics engine does lots of complicated things, but at heart, it's basically iterating through high school physics, right? F equals ma. Everybody remember that? So if we turn it around and you have instead acceleration equals force divided by mass, the physics engine knows the masses of all the objects, and you can also create complex objects in which there are different mass distributions, and we'll get to that later as well. So the physics engine knows the masses in the system. It calculates all of the forces that are acting on all of the objects, and then divides them, which gives the accelerations for all of the objects. And those are linear accelerations, so how fast or how slowly is an object moving left and right, into and out of the screen, and up and down, the 3 linear accelerations, and also 3 rotational accelerations. So how much is the robot yawing, pitching, and rolling? So how much is it turning this way, and this way? Did I get them all? Yaw, pitch, and roll. So we get back 6 numbers for every object, which we can then use to calculate the new position, or the physics engine can use it to calculate the new position and orientation of all the objects, and rinse and repeat. And you get, for example, if you place a sphere above the floor, that it will start to accelerate towards the ground and come to a sudden stop when it comes into contact with the ground. Okay, so what are all these forces that are acting on the objects? Well, I just told you one of them, right, which is gravity, pulling any objects down towards the ground. What other forces do you think the physics engine is simulating?
Motor forces.
Motor forces, right? The minute that you motorize one of the joints, that motor is going to try and rotate, is going to apply torque or rotational force that's going to try and pull or push the objects relative to one another. So there are external forces like gravity and internal forces like motorized joints. What other forces do you think come to bear in these physics engines?
Contact forces.
Contact forces, yeah, we're going to come to that in a moment. So gravity is pulling this object down, but the minute that it hits the ground is pushing with a reaction force to keep the object in place. So the reason that an object comes to rest in the physics engine on the ground is because the force of gravity and the ground reaction force equal one another and cancel out, and acceleration is 0 for the object. What other forces do you think come to bear on these objects that influences their linear and rotational accelerations? Torque? Yeah, so torque from where? We have torque coming from the motors. Okay. Yep.
Is there gravity in the system?
There is gravity, right? So we've got the external force of gravity acting on them.
We already talked about friction.
Yeah, exactly, right? So imagine that an object is not coming down perpendicular or parallel to the force of gravity, but is coming in at an angle. It's wrapped in carpet, if you like, or sandpaper. Comes in contact with the ground, and now it's still trying to move. Part of its motion is in this direction, but it's being opposed by the friction that's occurring between its own lower surface and the ground, right? So friction starts to apply drag force, which tries to slow the object down or causes it to start rolling. So there are a lot of these different kinds of forces that come to bear on each of these objects. That's how the physics engine calculates the new positions and orientations of the objects. Okay.
Would inertia be included in that as well?
Inertia is in there as well. Yeah. Okay. Inertia is in there as well. Okay, so throughout the rest of this lecture, I'm going to start to look at some actual code from Open Dynamics Engine. ODE is written in C, so if you're not familiar with C, not to worry. This should be pretty straightforward. We're not going to do anything fancy here. Again, you don't need to remember all this code. I just wanted to show you what's under the hood as you move forward with your assignments. First thing you do is when you send your system across and you send to PyroSim the command start, it will go through all of these preliminaries, which sets up the actual simulation itself. It creates a variable called world, and that variable is going to point to or contain all of the objects that make up the world. It also creates a contact space, which we'll come back to in a few slides here. A contact space contains all of the objects that should not interpenetrate. So within that space, at every time step of the simulation, the physics engine is going to look at every pair of objects, see where they are, and it's going to apply forces in these different conditions, right? The condition on the top there is okay. The position which can occur in the bottom there is not okay. So it will start to apply forces to push the ball and the floor apart. The floor will not give, and the ball will, and it will resolve any of these interpenetration situations. Okay, so the space variable, or this hash space, is taking care of all of the collisions. The contact group is sort of a library of all object pairs that are currently in contact with one another. The minute they come apart again, it removes them from that space. So there's a lot of bookkeeping that a physics engine needs to do as we go. You can set the gravity, so you can simulate Earth, you can simulate the Moon, you can simulate Mars, you can turn gravity off altogether. And then we have some other miscellaneous parameters. I'm just showing you one here that has to do with friction. So we can set friction of the whole world or specific objects. Lots of things we can sort of fine tune as we go. And I have some pointers at the top of these slides to the actual C code if you want to go in and look at the nitty-gritty details. Okay, so we've set up the world. We've sort of set up the general physics that operate inside this world. And now, like in PyroSim, we want to start to send objects into that world. So every time you create a cylinder or a box in PyroSim, it calls this code here, which creates a body. So for every object in PyroSim, we're going to create two variables in the physics engine. One of them is called a body, and we're going to see the other one in a moment. The first one contains all of the mass information. So we're going to set, in this case, we're creating a box. We're going to create a 1 by 1 by 1 kilogram box. I'm sorry, I think that's right. So that's the distribution of mass within the object. There's the fourth number here, which sets the density. We can adjust the mass a little bit if we want. This is just some old code that's sitting in here, but we're setting the mass of the object and how that mass is distributed inside the body. We're then setting the position of the object. You'll notice that we haven't set the size. We haven't set the length or the width or the height of the object yet. We're just setting physical properties and where it is in the world. That's a body. We can also specify the orientation of the body, and there are different ways to do this. Yeah.
Well, wouldn't that sort of specify the size to some extent because it specified the density?
Yeah, a little bit. So that's actually, I'm sorry. So line 7 here, what it's really doing is setting the mass distribution inside the body. We haven't said how big the body is yet, which seems a little strange.
So the mass, so it calculates it from the mass distribution, and the size calculates the weight.
We're going to set the size of the object in a moment. But in the physics engine, this is separated. So in PyroSim, you send the size of your object, the length, width, and height of a box, and then we assume a uniform distribution of 1 kilogram of mass inside that object. Okay. So we're sort of simplifying things for you on the PyroSim side. Okay, so we've set the position, which is the position of the center of the object, and we can also set the orientation of the object, and there are different ways to do this in three-dimensional space. Some are easier and some are much more difficult. The normal way this is done in the physics engine is using a quaternion, which requires 4 numbers. Quaternion basically takes your object and 3 of the 4 numbers, x, y, and z, set the long axis along which the object lies. So imagine we have a 3-dimensional object like this. We define a 3-dimensional vector, and we then lie the object along that vector. And then the 4th number specifies how much we're rotating the object around that long axis. Okay. Gets a little tricky. So in PyroSim, we've simplified this. We've thrown away the quaternion, and all you're going to specify is the x, y, and z vector along which your object lies. That's why in the assignments you're creating 2 cylinders rather than 2 rectangular solids, right? Because if we lie a cylinder along this orientation vector, then it doesn't matter how much it's rotated, right? Because it's a cylinder, it's symmetric around its long axis. So if you want to later on in the assignment, if you want to create rectangular solids and angle them in PyroSim, you can. The only thing you can't do is set how much a rectangular solid is rotated about its long axis. It's a bit of a cost we have to pay for PyroSim, but it's worth it so that we don't have to deal with quaternions. Make sense so far? Okay. Okay, so as I mentioned, when you create an object in PyroSim, it gets sent across to the physics engine, ODE, and each object is then specified by two data structures in ODE. The body, which we just described, which is mostly the physical properties, mass distribution, where the object is, and its orientation. The second data structure that's associated with each object is a geom, for geometry, which you can think of as the skin that's wrapped around the object. It's the geom, which is the thing that's drawn in the physics engine that you actually see. Okay. The geom is important because it's going to be used to specify how objects collide with one another. So if I am creating a box, when I create a geom, I'm placing that geom in the space, and it's going to have a length and width and height of 1. Distance units in a physics engine are somewhat arbitrary, so you can think of this as 1 meter, 1 centimeter, 1 foot. Doesn't really matter for our purposes. Okay, so we have a cube. We're specifying a cube here, and then we link the two data structures that describe that object. We're linking the geom and the body together. Okay. So now with these geoms, at every time step of the simulation, it's going to take the skins or the geoms of all the objects and determine whether they're colliding or not. And it turns out that that particular calculation is the most expensive calculation in the physics engine. So you can take the code that you have at the moment and you can send 100 objects across. You can create 100 random objects and drop them into your PyroSim simulation. And depending on your laptop, it'll start to slow down pretty quickly when you get to 100 or 200, 300. For most of you, it'll probably be pretty hard to get to 1,000. The thing that is starting to slow down your machine, the limiting step here is calculating contacts, and it's pretty easy to see why. Let's start actually with this picture down here. Let's imagine we've dropped 9 cylinders with 0 length, so we've dropped 9 spheres into our physics engine. How many contact computations does it need to perform?
Which picture are we talking about?
I'm talking about this picture down here. We have 9 spheres. 9 choose 2, which is? 1/2 of?
minus 1.
So,
9 factorial divided by 7 factorial over 2 factorial.
yes, we can do it that way. Let's do it a little simpler. Let's take this one. We need to see if this sphere here is in collision with the other 8 spheres, right? Is it in contact with this one? Is it in contact with this one, this one? So we need to do 8 calculations. Then we need to visit this one, right? And we've already done this calculation, so we only have to do these 7. So a good way to think about this is we have 9 objects. We could take each of the, if we were lazy, we could take each of the 9 objects and compare it to the other 8. So that's 9 objects times 8 calculations for each of the 9. 9 times 72. But it's symmetric. When we compare this one to this one, we don't need to do the other one. So we can take the 72 and divide by 1/2. Right? So we have n objects. We're going to do n times n minus 1. We're going to compare each of the n objects against the other n minus 1. Divide by 2. Pretty simple, right? So what is that? 36, right? So there are 36 calculations we need to do here for our 9 objects. If we have 10 objects, 45, right? It starts to climb very quickly. All right, I'll leave it to you to figure out how quickly it climbs, but it gets pretty hairy pretty quickly, right? So if you drop 1,000 spheres in there, quite a few calculations that it needs to do. Okay, so I mentioned this idea of collision spaces, which we saw in the preliminaries here. So here we're setting up one collision space, and typically again, this is the default in PyroSim, there's just one space and all your objects are being placed in there, which is good news for you because it keeps things very simple, but it's bad news for the physics engine because it needs to look at every pairwise collision. So when you get to the final project, if you find that you're creating very complex scenes with multiple robots and lots of objects out there in the environment, come and see myself or the TA, and we'll talk about creating multiple contact spaces, which makes your simulation run much faster. So in this case, we're going to assume that there are subsets of objects which only rarely come into contact with one another. So imagine we have two robots, and for any one robot, if it's moving its arms around, it might collide with itself quite often. So all the objects that make up robot 1 should probably be in the same space. We need to do all those calculations all the time. That's robot 1. Robot 2, which is 3 body lengths away from robot 1, might have a different body. It may be made up of more or less pieces, but it's also moving around, and it may also be colliding with itself and other objects in the environment. So we put all of the objects that make up robot 2 in another contact space. So most of the effort here is then going on within these spaces. So here we have 9 objects, and here we also have 9 objects. We know here we need to do 36 collision calculations. How many do we need to do here? Only 6. How many do we need to do over here? 10. So 10 plus 6, we can get away with 16 calculations here rather than 36 over here, and things go much quicker. There's a little bit of an overhead we need to deal with here, which is the physics engine is going to take these 2 sets of geoms, these 2 different sets, and it's going to wrap a bigger geom around both. And from time to time, look if those bigger geoms are colliding with one another. So if we have 2 robots and they're moving around and they happen to come near one another, now the physics engine says, uh-oh, these spaces are getting close to one another. I can't get away with just doing 16 calculations. I'm going to do all pairwise comparisons of all the objects inside these 2 colliding hypergeoms, if you like. Make sense? Okay, so I just wanted to go into the basics of that to give you a taste for how complicated this can get. So there's active research going on in computer graphics and computational physics about how to actually make collision detection when 2 objects come together, and resolution, what do you do when they do collide, to deal with that. Up till now we've been talking about spheres, which are the simplest possible objects to deal with. Because when they collide, how do they collide? Point by point, right? No matter how the spheres are rotated, if they collide, there's exactly 1 point, assuming that they are non-deformable, that they're maximally rigid. There's only a point where they touch, right? You can make rectangular solids. You can connect rectangular solids together. You can make very complex objects. What happens when those 2 objects come together? Right? Sorry?
Face by face.
Face by face, yeah, there's lots of different ways to do it. So up till now, we've just been talking about a collision computation. I haven't told you what that computation actually is. But when you have more and more complex objects that approach one another and possibly touch, those individual computations become very expensive. And those very expensive computations can go up superlinearly, so they can go up quadratically as the number of objects themselves increases. So things get very slow in the physics engine very quickly. For our purposes, you probably won't come up against that, but just wanted to point that out. Okay, so I mentioned contact detection. So are 2 objects in collision with one another or not? And then contact resolution. So are they in contact? And if they are, sometimes they will interpenetrate and we need to actually push them apart. Why would objects interpenetrate? That seems odd. We could obviously create a simulation in which at the first time step they are interpenetrating, which is exactly what happened when you created your scissor robot, the red object and the white object, right? Their 2 end caps are overlapping one another. But you can also have 2 separate objects that as they're moving end up interpenetrating. How can that occur? Yes?
Simulating like 2 tennis balls, like hitting each other.
We could, right? So you can actually exploit that fact by approximating soft materials. Assuming we don't, imagine in our physics engine we have 2 ball bearings and we're simulating them. You can actually get into a situation in the physics engine in which the 2 ball bearings are partly interpenetrating, which clearly is not physically realistic, and you want to push them apart as quickly as possible.
Could this be maybe they're coming at each other really quickly, and then so like it says, I'm gonna move a foot this way, and this one's half a foot here, and the other one says, I'm gonna move a foot this way, and then the next step, you realize, oh crap, they're overlapping.
Absolutely, that's exactly it, right? So remember that at root, at heart, our physics engine is a discrete simulator. From one time step to the next, the objects are actually jumping in space, right? Their positions are changing. It's not a continuous simulation. It may look like it. Physics engines were designed for video games so that if you have a high enough frame rate and a fast enough computer, it looks continuous. But obviously it's not. We're approximating this discretely, so you can have objects which are very small or are objects that are large and moving very quickly, where at the next time step, at one time step they're apart, one time step they're apart, and at the next time step they're interpenetrating. So collision resolution is the second part of dealing with collisions, which is to say, push them apart. Okay. As they're pushed apart, at the next time step, they might actually separate, and if gravity is acting on them, they update again, and you usually get something that settles down and comes to a stop. So when you place an object above the ground in PyroSim and you drop it, you may not actually see it, but it actually does interpenetrate the ground and then pop back up very quickly. If you have a slower computer, you might actually see this happen. But hopefully it's fast enough that it looks like the object is accelerating and then comes to a sudden stop, or it bounces a little bit when it hits the ground. Yes.
So a question that I had, when we were
Sure.
doing that, the objects didn't jump apart when we set them interpenetrating. So if you set them so that they're overlapping, does it not, does it say, well, okay, these can overlap?
Try it. So take the simulation that you have right now and comment out one line, which is the line where you create the hinge joint connecting them, and run your simulation and watch what happens.
Doesn't it just fall straight through since they're
Yeah,
not?
it just goes.
Oh, I'm sorry, we made a recent change to it. That's right, exactly. So pairs of cylinders, I'm sorry, that's right, this is a new thing. We set that up where pairs of cylinders, we turn this resolution off, just so we don't get into some of those problems. You can turn it back on again if you want.
Does PyroSim adjust the time step that it calculates when objects are moving faster or slower?
That's a very good question. Let's see, we're gonna get to that. We'll come back to that in a couple slides. Okay, so we just talked about collision. Okay, so let's talk about joints now. I think you already kind of know how this works. This one, at least under the hood, is simpler than the objects themselves. Whenever you create a hinge joint, and as you will see in later assignments in the final project, there are other kinds of joints you can create. We obviously need to tell the physics engine what are the two bodies that are being attached. We then need to set the anchor. What is the position at which we're connecting the objects? And finally, what in ODE is called the hinge axis, but for you it's called the joint normal, which tells the physics engine how the two objects rotate relative to one another, right? So this is a hard thing to do in 2D, but if we have two objects that are attached together like this, and we define a vertical joint normal, we call it the normal because that vector has a plane which is normal to it. And so the vector is saying, I want those two objects to rotate through the plane that is normal to the vector, right? So we can take the same two objects over here, or I guess this is the same picture, I'm trying to show this rotation, right? We could then, let's see, place the joint normal like this. So we have the same two objects. Now we have the joint normal pointing into the screen, and our two objects will rotate through this plane relative to one another. Right? Once the simulation obviously starts going, that vector is going to change. So it's basically just saying what's going to happen at the first time step, and the physics engine will take it from there. Right? As the whole thing starts moving, that plane is relative to the two objects. Okay, I think that one's pretty straightforward. Okay, so now let's come back to contacts for a moment. Inside ODE, there's some relatively complicated C code because part of the C code is event-based. So what that means is normal code, it executes one line after the other. In the physics engine, it's doing the same thing. It's executing one line after the other, but every once in a while in the virtual world, an event happens, and that normal processing is paused or interrupted, and the program counter jumps to a new piece of the code that can handle that event. So when that event happens, it triggers what's called a callback function, and in this case, it's a callback function when two objects get near one another. So we don't even have two objects that have collided yet. We're just saying geom01 and geom02 here seem to be getting near one another. So what are we going to do about it? First thing we're going to do is to determine whether we need to do anything about it. So in the code at the moment, it's set up so that if the objects are connected by a joint, doesn't matter. We just ignore that situation. Right? So objects that are connected by a joint, they often are already interpenetrating one another, like your red and white object, so we can ignore that. As I just mentioned, we added some new code recently where if both objects are cylinders, we also disregard the collision, just to keep things simple. So there's lots of situations where we might not actually want to resolve the potential contact at all. Okay. Assuming we do want to deal with the collision, how do we do it? So we now have two objects that are sufficiently near one another that we want to try and model the contact itself. So as we just mentioned with two spheres, usually they come in contact with each other with a point. Let's look at the slightly more interesting situation of two rectangular solids. In this case, they're approaching one another with two of their faces. And as they get close to one another, we call some code which will basically sprinkle points across the space where they are near or actually colliding with one another. And the reason we're going to sprinkle these contact points is that often the surfaces are relatively complex. Right? So sometimes they might line up, they might hit each other with an edge or a vertex or some combination. We might be simulating tennis balls, they may be deforming a little bit. It gets very complicated very quickly, so we're going to just approximate this. We're going to take these two objects that are near one another, we're going to look at their skins, or the physics engine is going to look at their skins, and it's going to take the subset of the two skins which are close one another and just sprinkle them with points. You can set the number of points that are used to be less or more. Why would you want to do that? Why does that matter?
Precision.
Exactly. Well, why don't we just be very precise? Why don't we, every time two objects are close to one another, why don't we just drop 1,000,000 points?
Well, I mean, like, for our assignment, we had two joints that were sort of the cat going in and out of each other.
The two objects, yeah.
Yeah, so maybe we want to simulate that.
Possibly.
Speed.
Right? Everything in a physics engine always is a trade-off between precision and speed. You can make PyroSim approximate the physical world arbitrarily closely. You're just going to have to wait a while for it to do so. So again, the default setup in PyroSim is it's not very realistic at the moment, right? You have these two objects that are partially interpenetrating basically all the time. But it's pretty fast, right? Okay, so again, depending on what you're trying to do, you can start to play with this antagonism between precision and speed. Okay, so depending on what you're doing, you might pick more or less points. This is mostly taken care of for you in PyroSim. Okay, so just to show you some code, what happens is when we do this, max contacts is the total number. So in this cartoon example, it's just 4. We have these 4 points, and in this cartoon example here, these 4 points fall right into space, and each one applies a little bit of forces to the two objects, pushing them apart, right? And remember that the physics engine is going to accumulate all of these forces. There are the force of gravity that's pulling these two objects down, and now there are these 4 points which are also applying forces that push them apart. So at the next time step, if they're falling and touching, they will move down and to the right. If they're on the ground, they might jitter a little bit and move a little bit apart. By setting some of the properties of these points, we can simulate different kinds of friction properties. So you were mentioning about setting friction. So you can set the properties of these contact points to simulate two ball bearings steel ball bearings coming into contact, two tennis balls, two wooden balls, two ping pong balls, you name it, you can probably simulate it. For our purposes, again, we're going to assume all of the objects just sort of have high friction, and these parameters have all been set for you. Okay. Finally, the last step in this near callback function is for all these contact points, we're going to create at that point a new kind of joint. So at the moment, you've only seen hinge joints. There are these odd kind of ones called contact joints. Why are they joints? Well, as I mentioned at the beginning, any kind of joint in a physics engine constrains the relative position and the relative orientation of objects in the physics engine, right? The hinge joint constrains the fact that they cannot separate from one another. It constrains their relative position and also constrains their relative orientation to stay within a two-dimensional plane. This is my normal, I can't rotate the two objects out of the plane.
Can you have objects connected by multiple joints?
You can have
So you can go on a
objects
shoulder.
connected by, absolutely. So in this case, we now have 4 objects which are connected, which seems weird because we're trying to push them apart. But for a brief moment in time, these 2 objects are connected by these 4 contact points, and they constrain, what these points do is constrain the relative motion of these objects at just the next time step. So unlike your hinge joint, which exists throughout the simulation, at every time step of your simulation, these contact points are going to come into being for one time step, constrain the objects, and then be deleted again. How do you think these contact points constrain the relative position and orientation of these objects? What are they trying to stop?
Sliding.
Could be sliding, right? So they're high friction, so we want to try and stop this motion, relative motion. Most importantly, they're trying to stop this motion, right? So perhaps these 2 cubes were speeding along the ground towards one another and collided at a high velocity. There's some interpenetration. These objects, because they have mass, have inertia and momentum, so at the next time step, they're probably still going to be trying to push against one another. So the contact points are saying, stop, stop, stop. We're going to try and constrain the position towards one another, and they're going to constrain it by applying forces that push in the opposite direction. Yes?
So I'd imagine in like the real world, if you had 2 cubes
Yep.
that were maybe soft, coming towards each other, and they hit at a high velocity, they might change shape somehow.
Yes.
Is that possible to simulate?
That is not possible in PyroSim. So PyroSim is a rigid body simulator, right? So you can approximate 2 soft objects kind of by allowing them to interpenetrate and then push back, but you cannot deform the shape. That's a good question. Towards the end of the class, we're going to talk about soft robots, and you're going to see a soft-bodied physics engine, which does allow deformable shape changes. If you think PyroSim is a computational hog on your machine, wait till you try a soft body simulator on your machine. Things get really computationally intensive, and we're not going to go into that in this class. Yes?
Is it possible that the 2 objects are going too fast and they just go straight through each other?
You can do it, absolutely, right? Especially when you start to build more complex scenes in PyroSim, you will start to see some very odd behavior, which you don't usually see in the real world. If you shoot 2 bullets at one another, you can get them to actually miss one another if they're traveling at a high enough velocity. Absolutely.
Can you create something kind of like a sculpture in PyroSim? So like if you had a sculpture of a man, the arm is attached to the body, right? So there's a joint there.
Yep.
But if it hits the ground, you don't want it to bend in. You want it to, fall
Yeah,
rigid.
Absolutely. So you've already seen, yep. So you want to build a statue. So something that's a complex object made up of a lot of simpler connected objects.
Yeah.
Absolutely. Instead of connecting the objects with send hinge joint, you connect them with send fixed joint. So if you look in the documentation for PyroSim, there's a fixed joint, which basically just welds the 2 objects together. Yeah. Yes?
These cubes are like contacting on the same plane, like
Yep.
they're all on the same plane, but what if like your surface that hits a flat surface isn't a flat plane? where do you choose to put the contact points?
Okay, so let's have these two objects collide. They collide and perhaps they touch at a point. Is that the case you're talking about, or an edge?
Yeah.
Right, so there's really three cases, right? Face, edge, or vertex. So depending on the relative orientations and the relative positions of the objects, remember that ODE knows the positions and orientations of both objects. It approximates where they're touching based on their geoms, their shapes, and their relative position and orientation. So it approximates that shape and then just drops some points in that shape. So it might not go to the effort of actually calculating the exact vertex at which they collide. It could do that, but that's very computationally intensive. So it approximates it. It says, given their positions and orientations and accelerations and geoms, their shapes, I know the collision, if it's occurring, is about here. So I'm going to drop some points in there and apply forces that push the objects apart at that point. Or, not at that point, but in that local volume.
Given it's approximating, do you know, like, roughly the error, like, compared to the world that it's doing?
So what is the error relative to what would actually happen in the real world? It's set up in this way that with more contact points and a more accurate physics engine, it approximates the real world. And you can actually go into the documentation and see how much computation you need to approximate the real world. That gets complicated. I'm not going to get into that too much. Yes?
So when you talked about bridging the reality gap,
Yes.
would you say that that problem is the result of the sum of every single place where we choose like performance or decision?
Absolutely, right? So at all these points along here, we are striking this balance between precision and speed, and every decision we make is false. It's not what actually happens in the real world, and those approximations start to add up. So you're talking about the reality gap, where we evolve a simulated robot and then transfer it into a physical robot, and often we fall in the gap. What we evolve doesn't work in reality. Yes, because of each of these decisions. So one solution is to try and do a better job of simulating the real world. That's one possibility. There are other possibilities where we actually go in the other direction. We make things worse on purpose, which seems anti-intuitive, and we'll come back to that when we talk about the reality gap. But yes, all of these decisions we're making is why the reality gap exists. Right? Okay, so all of this is sort of build up to the most important function in the physics engine, which is the simulation loop itself. So just to refresh your memory, we did the preliminaries. We set up the physical properties of the world, how much gravity there is. We've added all the objects and joints into the simulation. We have this near callback function, which is sitting there and waiting, and it's called into action whenever pairs of objects approach one another. Then we enter this simulation loop. We pass through it. We go back to the top, and we loop through this simulation loop however many times you want. So in Pyrosim, when you say eval time equals 100 or 1,000, what you're saying is how many times you're going to iterate through the simulation loop. So what happens? Well, at the beginning of each time step, we look to see whether any objects are colliding. So we say, hey, near callback function, there are these pairs of objects which are near one another. Go check it out, and if you need to, add your points and add any forces to the simulation that are required, right? Add some forces to push any objects apart if needed. So what's actually occurring throughout this pass through the simulation loop is we're going to start adding a bunch of forces to all of the objects. Near callback gets first dibs. It adds its forces. If the simulation is not paused, we step the world. And this is probably the most important step. This is the one where we call A equals force divided by mass. This number here, it approximates the amount of time that elapses from one time step to the next, and this is in seconds. So we're telling the physics engine to step the world, update the new positions and orientations of all of the objects, assuming that 0.05 seconds have elapsed inside this virtual world. What do you think happens when we send a larger number to world step? What does that mean? What happens to your simulation? It's less accurate, right? So you can actually try this. Actually, I don't think you have access to step size in Pyrosim. I have to go back and check. But what happens is if you have a large number, you'll see the objects jumping from place to place, and it looks like you've hit fast forward on your simulation. The robot will have the chance to move much faster and probably move much further than it would normally. But you'll start to see more and more of this weird behavior, like objects passing through one another. If you have your scissor robot moving around, sometimes it will actually fall through the floor. It happens to jump, and then it's approaching the floor at just the right position and acceleration and orientation that near callback misses the near approximation, and through the floor it goes. The closer that number is to 0, the less time that elapses between one time step and the next, the slower your simulation will run, literally, but the more accurate it is. So all of these parameter settings set how realistic or not your simulation is, but the most important one is this world step. The way it's set up for now for the class is it's a static time step, so it's always 0.05 seconds. Someone was asking about dynamic tuning of the realism. There is an alternative call inside the code that will dynamically set this number depending on what's going on in the simulation. Given that dynamic simulation, when do you think the dynamic simulation would want to set a smaller time step? What would be going on in the virtual world where it says, wait a second, let's slow everything down?
Objects are moving faster.
Objects are moving faster, right? It detects high acceleration inside the physics engine, and that's when the physics engine has to be particularly careful. Yep.
Or if there's like no objects moving, you could like speed things up.
Absolutely, right? So all of the objects have sort of slowed down and come to rest. Now you can get away with speeding things up. What else?
Objects are closer to each other.
Exactly. So near callback might put up its hand and said, whoa, there's lots of objects that are very near one another, especially then you want to slow things down, right? They may be near each other, and in worst case scenario, they're near each other and approaching at a very fast velocity. You have two bullets that are approaching one another, very difficult situation to simulate realistically. Okay. Yes?
Oh, when you play that back in Pyrosim, will Pyrosim play back at every single time step, or will it skip through to keep a specified rate of time?
Here's your answer right here. So in the way this is set up in the moment is every step of the world, regardless of whether it's a big step or a small step, and for our purposes, it's a fixed step. Every time the physics engine steps the world, it also draws all the objects. So update the physics, and then draw, update the physics, draw, and repeat. You can, if you want, get into the C side, and you can play with this, so you can draw every other frame. So you can also speed things up on your machine by drawing every second, every third, every 10th frame, which speeds things up a little bit, but it doesn't deal with the underlying bottleneck of the simulation, which is near callback, or the amount of collisions. So even if you're drawing every other or every 10th frame, if you've got a complex scene, it's still going to run pretty slowly.
I'm just wondering if there's any way, if there'd be any way to take advantage of a computer's GPU.
There is. ODE was one of the first physics engines that was made. It's not GPU compatible. There is an alternate physics engine called Bullet, which you can play around with, and that one is GPU compatible.
So that would run a lot faster, I guess.
Depending on what you're doing. So there's certain physics for which the GPU helps, and certain other things like these collisions, which are a little bit harder, but again, you can still get a GPU to do it. Right? So we're now sort of talking about an entire field of computational physics and computer graphics and physical simulation, which is interesting in and of its own right. Okay, so in SimLoop here, they're really, for our purposes, And here's, sorry, just one last thing. Here's joint group empty. I mentioned that these contact points are created for just one time step. If they need to, they push the objects apart a little bit, and then we throw the points away. We assume at the next time step, there's going to be a completely different situation. It's going to require a different cloud of points. So these are temporary joints. Throw them away, and then draw all the objects in the scene. So update the physics and update the scene visually. There is a third thing that your assignment is doing, your code is doing, which isn't in the code here. What is that third thing? What's missing here?
Constraining rotation of joints.
That's all done here in D world step. So
Oh,
that's
it is,
all
okay.
done. That's all done here.
The controller for the robot?
The controller, right? So you may have noticed in our discussion today, there's been no mention of robots, no mention of sensors. We mentioned motors briefly when we said they apply these torques or rotational forces to joints. But a physics engine is not a robot simulator, right? It just simulates certain physical scenes. So what PyroSim does is add sort of the robot stuff on top. So there is these ellipses here sort of saying there's additional code. One piece of that code is to update the sensor values of your robot, push those sensor values along the synapses to possibly some hidden neurons if you have them, and then push those values down along the synapses to the output neurons. Take the values arriving at those output neurons, and those are going to be desired angles. Remember we talked about that. We take that number to desired angle and we send it to the motor. The motor takes that desired angle and turns it into a torque. So the further the current angle is of the joint from the desired angle, this difference, the greater this difference, the more torque that the physics engine applies to the joint. So ultimately what the brain of your robot is doing is taking information in from the physics engine, propagating it through to the brain, computing new torques, which are rotational forces that ODE throws on top of the objects and adds that to gravity, the gravitational force acting on the objects, any drag forces, if the objects are colliding and rubbing against one another, all the other forces, it just adds them to the pile. And those additional forces are used to update the new rotational and linear accelerations of the objects in the physics engine. That's how we combine the brain of the robot with the physics of its world. Make sense? Okay, so there's really three things going on that you should take away from this slide. Update the physics, update the robot's brain, draw everything, brain, physics, draw, brain, physics, draw. Around and around we go for 100 time steps, 1,000 time steps, and we're done. So far so good? Okay. Okay, so as I mentioned, everything up till now has been non-robotic. So you also are able to send different kinds of sensors from PyroSim to ODE. How did we get ODE to simulate these things? Well, we're going to simulate the sensors of the robot by exploiting the machinery of the physics engine itself. So I'm going to show you a couple of these and sort of show you how we do this. It's a bit of a black art, but you can probably start to figure this out. First one, and the most simplest one, is the touch sensors, right? These are kind of very simple sensors. So imagine we have this four-legged robot and we're looking at it side on. So we see its right front leg and its back right leg. There's a touch sensor in each of these two legs. The back touch sensor is firing because the back leg is in contact with the ground. And the front touch sensor is not firing because that leg is not in the ground. We put additional code in there that says the touch sensor does not light up just because one body part is in contact with another body part. That doesn't count. Okay. So remember that near callback will tell us when pairs of objects are in collision with one another. So we put some additional code inside the near callback function to say, if you ever get a pair of objects that are near to one another, and one of those objects is the floor, or basically part of the environment, and the other object is an object that has a touch sensor inside, which for us is just a variable, true or false, set that touch sensor to 1. If we get all the way through simulation loop, If we get all the way through sim loop and near callback didn't do that, then that touch sensor is set to 0. So we're exploiting the fact that the physics engine is already computing when pairs of objects are in collision with one another. So we can just piggyback our simulation of the touch sensor on top, right? Pretty simple. Okay. What about a light sensor? I don't know if we've got there in the assignments yet. Have you built a light sensor in your robot yet? Not yet. Okay, you'll get there. How does the light sensor work? Well, when you get there, oh yeah, that's right. I think it's assignment, we don't get there until assignment 10. So yes, you haven't seen it yet. In assignment 10, what's that?
There is a rangefinder.
There's a rangefinder, that's right. There's a ray sensor in assignment 4. The light sensor works as follows. You can place an external object in the environment, like the cube over there, object 4, and you can then set that object to be a light source. So we're setting it to be like a light bulb. So it's emitting a light. And then if you place a light sensor inside an object, inside one of the body parts of your robot, then when the simulation starts up at every time step, we can query the physics engine, we can get the position of object 1, we can get the position of object 4, and we can then take the Euclidean distance between the centers of those two objects, which is basically distance, and approximate the amount of light that's falling on the light sensor there. So the greater the Euclidean distance, the lower the light level. Yes?
Does that take into account like other objects being in the way?
Good question, right? So again, we're going to fail to cross the reality gap if we try and evolve a robot that's sensitive to light, because we're not dealing with occlusion here. There's no such thing as shadows or objects between. It's just Euclidean distance. So the light sensor, if the robot is just relying on the light sensor and there's the possibility of objects between the light source and the robot, you can be sure that's not going to cross the reality gap. There's other things we could do to help with that situation.
I think we might be past one conversation, but can you make surfaces grip more in the sensor, on the physics engine?
We are developing Velcro. It's not in there yet, but yeah, you can make things that actively grip. It's an active grip. We're trying to make that where it's passive or active. So you can cover your robot in Velcro so that if they come into contact, they stick. We're also making a passive Velcro. So you can flip it on and off, or the robot can flip it on and off with a motor neuron. So it's basically covering itself in Velcro or not.
How is that different from like friction? 'Cause I thought you said there was friction.
There's friction here, but objects can still collide. There's drag, but if they have enough momentum, they will just keep going. So Velcro is, no matter how fast the objects are approaching, if they touch, they will never separate again.
Are there magnetic forces in this?
Not yet. That's on the books. So we've got a list of things. We've got a to-do list of things to do.
Wouldn't that be like an easier way of doing that? Not easier, but like.
Yes, easier, but not easy. Let's put
Yeah.
it that way. Yes, could put that in. Okay. Okay, so back to touch sensors. This equation here was actually from an earlier version of PyroSim, and again, we've improved this. Any physicist here? How does light propagate?
Does it have to do with like the square of the distance?
Square of the distance. So again, if you go back to your high school physics book and you look at the propagation of light, it goes with the square of distance, right? So there's actually a raised to the power 2 in there somewhere now. So there's two things that are obviously already wrong with this light sensor. It doesn't deal with occlusions or being in shadows, and it doesn't simulate the propagation of light properly. Light does not fall off as it radiates away from this flashlight. But for most purposes, this will be good enough. Why do we have a light source and why do we have a light sensor in there? Because in PyroSim, with about 10 lines of code, you can build Bradenberg vehicles 2A and 2B, the aggressor and the coward, right? Okay. Okay, so that's motors. There are many more sensors that you can use. You already have seen the ray sensor. There's a bunch of other sensors in there. When you implement them in your assignments, given this lecture, think about how we might have approximated that sensor in ODE. You saw how we exploited the near callback function to make the touch sensor. We can query the positions of objects and how far apart they are from one another to approximate a light sensor. What are some of the other exploitations we might be able to make the ray sensor? And I think you've also seen the proprioceptive sensor, right, which sits at a joint and reports the angle of that joint. Given our discussion this morning, you can probably figure out how we simulate those different kinds of sensors. Okay, just something to think about. So let's switch from sensors to motors now. Again, let's assume we have our four-legged robot here that we're looking at from the side. How does this actually work? Well, let's assume at the moment that the front leg is vertical, but there is a motor neuron that is outputting a value of 60 at that black dot. So there's a rotational joint there, and there's a motor neuron attached to it, and that motor neuron is sending out a value of 60. It's saying, I want to rotate the front leg, relative to the body by plus 60 degrees. How does ODE do this? The first thing we need to do at each hinge joint is set a particular parameter, which is the maximum force that's going to be applied there. Remember that the physics engine is calculating the forces for us. We don't do that. We just sort of tell it what's going on, and it figures out the forces on its own. We want to make sure that it never applies some huge force so that the leg goes rotating fast and rips off the robot and goes flying off into the distance. That can happen. So we need to make sure that the motor has a certain maximum strength. We then tell the physics engine what the desired angle is, which we get from the motor neuron. We then query the physics engine to ask what is the actual angle. And in the cartoon here, in the top left, the current angle is 0. Take the difference between the two, so the difference is 60. The current joint is 60 degrees away from where we want it to be. We take that difference and we set the desired velocity of the joint. So the joint is going to start to rotate with a rotational velocity that's proportional to the distance, or the difference, I'm sorry. Why set the velocity proportional to the difference? Distance.
If you always say go this way, it might overshoot. You want to say like, oh, I'm 1 degree away, slow down so that the next time it'll stop.
Exactly. So the value that arrives at the output neuron, in this example 60, does not mean that at the next time step, the leg is going to immediately appear at 60 degrees. It's going to start to accelerate with a certain velocity towards that desired angle of 60. Let's assume in this cartoon that at the next time step, it's got 20 degrees of the way there. So this is a pretty fast simulation. It's usually maybe 1 degree or 2 degrees. But for our cartoon purposes here, it's reached 20 degrees forward. But imagine that the motor neuron, depending on the brain of the robot, hasn't changed. It still says, I want an angle of 60. So now the difference is the desired angle of 60, the actual angle of 20, difference is 40. So the new velocity is going to be a little bit less, or the actual torque, the amount of rotational force that's applied at the joint is going to be a little bit less because we don't want it to overshoot. The next time step, actually if I was doing this right, it wouldn't be 20, it would be maybe 22 or 23 because there's less force being applied, so it got less of the way there. So the difference will start to decrease as time goes on, and if the motor neuron is constant, the leg will rotate and come to a stop 60 degrees in front of the body. Yeah. One thing to keep in mind when you start to make a complex simulation, we're going to adopt an arbitrary convention, which is that whenever you connect two objects together, the default is always 0. So if I create two objects in the simulation like this, the relative orientation between this object and this object is 0. If I create a simulation with these two objects, the relative orientation between them is still 0. Obviously, that's a little bit non-intuitive because obviously these two relative orientations are different, but we're just going to use that convention where this is 0. And then as the joint starts to move, any joint that pulls objects in towards the body is flexing, and those we're going to assume are negative numbers. So, and anything that's a positive number, like you see here, the desired angle is positive 60, means extension, that the objects are sort of moving away from the body. It's arbitrary, it could be something else, but as you're setting your joint normals and figuring that all out, make sure that that's the case. Okay. Okay, I think this is the last two slides, which is perfect. We'll just get through that. Okay, let's add in the last piece, which is the neural network. Today we've seen objects, joints. We've just seen sensors and motors. Remember, our neural network connects our sensors to our motors. How does that work in the physics engine? So let's put all this together now. We have two touch sensors. Let's assume at the beginning, both legs are on the ground. So T1 equals 1, T2 equals 1. They're both firing. These two touch sensor neurons are connected by synapses to one motor neuron, which outputs a value of 60. I haven't told you what the synaptic weights are here, but we'll come to that in a moment. As we just saw, at the next time step, that means that the leg is going to rotate 20 degrees, is going to extend 20 degrees away from the body. The moment it does that, because this is an embodied agent, remember, an embodied agent, the moment it moves, it senses a sensory repercussion of its action. The moment it moves, T2 goes to 0. So the values at the input layer have suddenly changed, like we saw when we were looking at the truth tables. And now the new value of M1 is minus 90. So this is T0, time step 0, time step 1. What happens at time step 2 now? It's going to start to flex the leg back in with even more force than it just did at the previous time step. Okay, last thing for today. Let's assume that there is no activation function at this output neuron. Forget activation functions. We're not going to squash the value. We're just going to take this times this plus this times this to get this. So we're just going to try and figure out what are these two synaptic weights. And those two synaptic weights also have to mean that this times this plus this times this equals this. What are the two synaptic weights? They're also now not between minus 1 and 1. So it's obviously easy to deal with this one, right? Because since this is 0, you can forget about this synaptic weight. We need 1 times x to equal minus 90. So x is minus 90. So we know this synapse is minus 90. So 1 times minus 90 plus 1 times y is 60. So it's 150. That's right. Okay, so this neural network with these synaptic weights will produce this movement in this toy robot. That's connecting robotics with physical simulation. Perfect timing for today. It's Thursday. You have a quiz due tonight. If you have time tomorrow, come and hear something about gene therapy at John Dewey Lounge at noon. Have a good day. Yes.
I don't know much about this. I haven't taken much.
That's all right.